So welcome everyone. This is the first and the introductory lecture on programmable logic controllers, and the title of this course can go as Introduction to PLCs or PLCs only, like in this case, or some other variations as in the title or in the course title with the keyword PLC in it. So as an introduction level, if you really want to um, kind of get hands-on skills and learning on PLCs. So this is the course today. Okay, so in this particular course, we will be following this book, which you can see here, the Programmable Logic Controllers, written by Max Rabai, and it's very popular, kind of a industry accepted. When I say educational industry, different institutes, colleges, universities, where they will use this book in their curriculum. And we are going to do all the course coverage from this book, assignments, labs, and presentations. Majority of it will be from that book, like this presentation. So let's carry on with PLCs. Okay, so we will be covering the chapter 1 of this course. Okay, so the most important thing right at the beginning, if you have never heard about PLCs, or if you have heard about the word or the keyword PLC, but you don't know what it is, what it does, so it's very important to be very clear in the beginning, like lectures like this one, and ask questions if you're still not sure about it. So here's a video. So let's see this video and be attentive to all the words said, and please note down any questions you have to be asked. Okay, so let's see the video.
A programmable logic controller, or PLC, is a computer that's designed to control and automate processes, typically in an industrial setting, but is used whenever you're looking to reduce human interaction and increase precision and efficiency. With PLCs, all your real-world inputs and outputs can be directly wired into the PLC, eliminating a lot of unnecessary control devices, which will save you money and greatly reduce your circuit complexity. And when it comes time to modify the control circuit, changes are made in the PLC project without the need to rewire your control cabinet, and can be done as fast as just making a few changes in your PLC project. For example, let's say we have these three motors and you want one push button to turn them all on. This can be done by using interlocks on the contactor. But if you need to make any changes, like staggering the motor start times, or even having defined run times on the motors, this can quickly get out of hand and require a lot of extra hardware. With using a PLC, you just wire everything into the PLC, and you can add contacts and timers in your ladder code, update the PLC, and as quick as that, your new process is up and running. Modern PLCs typically store the entire project in memory using common, industry-standard programming language, so you never need to worry about losing the knowledge and work that went into creating the circuit. Anyone familiar with PLCs can figure it out and debug it. What makes PLCs different from other controllers is that it's designed for the rigors of the industrial world. PLCs offer superior longevity and are typically supported for 20 to 30 years, meaning you'll always be able to get spare parts and programming software that work with your system even decades later. Try that with a traditional PC. PLCs are easily expandable by adding more modules, so you can expand your system without having to replace it whenever more I/O capacity is needed. PLCs are available in many brands that have their own feature sets.
So this is the next. It's about they are going to market their own kind of PLCs, what they represent. But the keywords, what you can understand from this video, or the key knowledge, is that the PLC provides you flexibility, cost effectiveness, and efficiency in implementing your processes, your tasks, your smart system in the industry, depending on whatever task you've been given on it. But as we mentioned before, historically that wasn't the case, and it was quite cumbersome, costly, time consuming. Okay, so hopefully that clarifies what is a PLC, and let's carry on with the next slide. Okay, so now with the basic understanding on the PLC, now it's important to understand what are the major players in this industry, the manufacturers of PLCs leading the industry globally. So, so what you see in the slide is kind of PLC manufacturers, but among them, these like Siemens, Rockwell Automation, Allen Bradley, ABB are the leading companies in PLC market out there. But some other competitors like Schneider or BNB, BNR, or Mitsubishi, and Toshiba. Like there are some other companies, being very good competitors in this marketplace. Okay, so let's carry on to the next slide. And that's how the PLC looks. In the video you have already seen it, but again there are different variations, look and feel of the PLCs, how they look like. And so these all initial slide is to give you a clarity on what a PLC, what it can do, how it looks like, what are the leading manufacturers. So let's carry on now to the inside details of this particular lecture. Now there are the objectives, as you can see here. So in this particular lecture and subsequent one, we will talk about the history and the development of programmable logic controller systems, discuss the benefits of PLCs, which we have already learned about it over electromechanical relays, distinguish between fixed and modular PLCs, we will learn in this lecture, describe the functions of central processing unit, also called as CPU in a PLC, explain different types of memory devices and their use in PLC systems, explain the use of the address decoder circuit in a PLC system, we will learn in this lecture, and describe the differences between discrete and analog input and output modules. Okay, now discrete means digital, you can think of this as digital inputs, and analog is the analog inputs or the output modules in both categories. List the major components of a PLC power supply. Okay, we will learn this in this lecture. Describe Allen Bradley programmable controller devices. Again, kind of a leading brand manufacturing PLCs. Compare the various type of Allen Bradley PLCs. Describe other type of industrial controllers and compare them to the PLCs. Describe the expansion and use of communication with intelligent industrial controllers. So these are the objectives of this lecture and the subsequent one we will try to cover. Okay. So a PLC, all devices have discrete inputs and discrete output ports. Okay. Larger, more advanced PLCs, can have variable inputs and variable output ports, and we will learn shortly what that means. This is what the PLC block diagram is. Okay, so as you can see here, it has a power supply, it has an input module, the digital one, the discrete one, and the output module, the discrete or digital, or it can have input-output modules for the analogs as well. To make this diagram further simple, so I have redrawn it like this, as you can see here. So in this simplified, you have inputs and you have outputs, and the power supply, as in any other electrical electronics system, we need it. And so the inputs can be analog or digital, and the output coming as is analog and digital. Okay, as you see here, there are kind of arrows which are solid, and here's a dotted line. as a feedback arrow. So in some cases, you may want your analog or digital output to come back as an input to the CPU, depending on your task. So that is the reason of putting that dotted line. So not necessarily you always need it to use the output as your input, but in some cases, in some tasks, in some processes, you may require it, and that is the reason of showing this um, feedback line. So it's very important that you understand these block diagrams, and you can be asked to draw it. That what is a PLC block diagram in your exams and tests. Okay, so make sure that you'll be very clear and be able to draw such block diagrams. Let's carry on. So one of the type of PLC is called fixed PLC. So in the fixed PLC, as you can see here, this is the PLC, and Alan Bradley and the model of that PLC. So why it's called fixed? Because all units are in one fixed enclosure, and the number of input ports cannot be expanded, and that's why it's fixed, and the number of output ports cannot be expanded. So typically it's at one location and fixed number of input ports and output ports. So for example, in this particular example, let's say you were using this PLC has, let's say, 10 inputs and 10 output ports, and you're using it for some process, some need. But all of a sudden, if in future all of a sudden you require 50 input ports and 100 output ports, so this PLC is not going to solve the problem. So because it has only limited number of inputs and outputs. So for that, the recommended, if you intend that in future a scenario might can change, so the best is to go for the modular PLC. So what is a modular PLC? Each unit is placed in a different rack. Input modules can be added if needed, and output modules can also be added on a modular PLC system. That's what it is. That's why it's called modular. For example, in the beginning, you only need one PLC like this one, and there was no other PLC. But as the needs arises, you are adding more PLCs in the modular system. Since they have a backplane, we call it as the backplane bus, which connects all the PLCs together with a centralized in a centralized fashion, and with the software, you can see those added PLCs, and you'll be able to use those additional resources for your processing, programming tasks. Okay, so that's the difference between a fixed and a modular PLC. Any questions, please note it down or ask right now or during office hours. So let's carry on. So now the most important aspect in using a PLC is that how we're going to program it. And you can think this as it's a graphical programming language, that it's not that you have to type in order to program a PLC, and that's why the symbols you see here, these are graphical symbols, and we will learn about it. So the inputs will look like this. Normally, the space is there, so that's why such inputs, let's say in this case A, and here is a B, and the output is Y. And because of the space, they call it as normally open kind of input. So that's why the normally open. And so normally open means A is false, B is false, and because of A and B is false, Y is false. Why? Because if you think this, the entire row as a wire, so the wire is green here, so there is a connectivity, so the current can flow here, but since there is a space, there is no connectivity, and hence there is no flow of current, and that's why the black color signifies it. And no current flowing here, and same here, no current flowing here, and that's why there is no current at the output. And that's why the conditions that A is false, it's open, no current flow, B is false, no current flow, and the output is false as well. So it's very important to understand this aspect of the representation, because that's what the programming the PLC programming signifies. So now let's say that now we come to the next example where A is false but B is true. Okay, so it means B is true means that it's connected now from here to there. That's why the green is there. So it's no longer normally open, it's closed. So the current can flow here, but the current is coming from the left side. So since there is no current flow here, even though it's connected, it's shorted. There will be no current here, and hence the output will be no current or false. So that's exactly this is the condition is trying to signify that A is false, B is true, that it's connected and shorted, but Y is the output is false. So now the third case is that A is true, that it's shorted and the current can flow, but since B is false, there won't be anything at the output. And the third case, now this is true, that it's connected, now it's closed, and B is closed, and that's why the current can easily flow from input to the output. And that's, in simple words, how the PLC programming look like, and that's how we are going to do PLC programming tasks. Another example here, just to further clarify it, same, but now in this case, now we have our inputs in parallel. Here the inputs were in series, but now the inputs are in parallel. As you can see here, now there are two paths. This is path number 1, the other path is path number 2. So A is again can be false, false, A is false, true. Since this is true, the current can flow from here and the output will become true. And now this is A is true, but B is false, but the current will flow from this path and go to the output and becomes as true. And the third case is both A and B are true, so current will be flowing to the output. But in simple terms, what we just learned is, in the first example, this is, if you have done programming, this is what we have done, that if this is true, but in this case it's false, so it's an if statement, that if whatever is the true or false condition, and because that's why it's a horizontal wire, so it's an and operation, and the B condition true or false, then the output will get affected as true or false. So because it's an AND operation, so as you see here that both of inputs A and B has to be true in order for output to be true as well. If you have learned basics in digital circuits, that I'm pretty sure you'll be very kind of clear on this, that this PLC programming example on the left side is basically an AND operation in the digital world, and here we are doing it graphically. On the right hand side, it's basically an OR operation because we have two paths, the top one and the bottom one. So that's why we call it as an OR operation in the PLC programming system. Any questions, please ask, or come see during office hours for any clarity. So let's carry on. Now we are going to learn the key kind of terminologies relating to PLC programming. So we have seen that on the left side there is a rail, which or there is a line, vertical line, goes from top to bottom. We call it as rail. Same here on the right hand side, vertical line or a bar, we call it as a rail, and all the horizontal rows are called rung. So in this case this is rung 1, rung 2, and rung 3. So these are rungs, and the input and logic expressions are on the left hand side and the outputs are on the right hand side, and we already talked about the symbols. Okay, and you can put comments for every rung or every horizontal line when you're programming a PLC. Okay, and you can give your tag name and every input has a tag name and the address. Similarly, every output has a tag name and an address if you want to give it. Okay, so that's um, and you can also, as I mentioned, you can put comments for every run if you need it. So with this said, there is one different symbol than what we discussed in our last slide is this one. So this is basically the default opposite of this is normally open and this symbol is normally closed. So what it means, so for example, by default this is a false, it means normally open condition, but the opposite of this condition is this symbol, which is true. So in the case of this, if this is true, the opposite of that is false, graphical symbol, but again, color also signifying whether it's true or false. So there is, common symbols, terminologies relating to PLC programming. So let's carry on. So in a PLC, CPU, or we call it as a central processing unit, is the brain of the PLC, and this particular block diagram signifies what are the main components inside the CPU. Okay? So it has the MPU, which we call it as the microprocessor unit, and again this MPU is the primarily is the main processing engine or the brain of the PLC. Normally, when we talk about CPUs, in general terms, we call it as the brain of a smart system. But inside the CPU, there are different blocks, as you can see here. And MPU, or the microprocessor unit, is the main unit, which is basically processing or executing instructions. And the other, it has memory, as you can see here. There are ROM, or read-only memory, or random access memory. We will learn about it, what is a ROM and a RAM. And there are other supported tricks like the one for generating the clock circuitry, or to decode the address, or for peripheral interface adapters, input buffers, output buffers. So there are different support ICs required in order to make the entire system work as a CPU. Let's go to the next one. So now let's go, what is an MPU? So there is a brain of the central processing unit, carries out or execute program instructions, and that is what its task is. Now we talk about the ALU. So inside, so here we learned in MPU. So inside the MPU, so this particular block diagram is the block diagram of the MPU. So what is inside the major components of an MPU? It has ALU, which is arithmetic logic unit, and ALU have registers. So as you can see here, registers. It has internal bus. It has instruction cache. You think that is the number of words, number of machine words an MPU can understand. It has the data cache and the control unit. Control unit is basically for the timing, that when to fetch a new instruction and how to execute it. That's the job of the control unit. So the register's job is to hold data for arithmetic logic units. So the important, we will learn about cache, but when we talk about the word instruction, I'm going to further go down in the subsequent slide. But again, what you see here is basically the block diagram or the major component inside an MPU, microprocessor processing unit. Okay, so make sure that if you've been asked to, some of the important key blocks inside an MPU, you should be able to answer that question. Let's carry on to the next one. Again, it's a control unit and the decode unit. We already talk about control unit, coordinates and controls all activities within an MPU. Decode unit translate instructions into a format that an MPU can understand, and what that means is we are talking about digital world. CPU, MPU, ALU. They are all basically it's a digital system. So digital system means they can only understand the language of zeros and one. So for example, if you're talking to the machine, okay, execute these instructions. Let's say we write it as a program, or we just talk on the mic. Either way, different mechanism you can tell a machine what to do. uh, that instruction or a task has to be converted into language of zeros and ones, and into the subset of instructions which MPU can understand, and only then it's going to do its job. And that's exactly what it happens, and we will further I'll show you what I mean for that. Okay. And the caches, why we use cache is basically to temporarily hold the instructions. The instructions most of the time they are stored in RAM, random access memory, but from there you fetch the instruction and hold it, on the MPU memory, the cache, so that you don't have to go far distance. It takes time. So if you hold instructions temporarily on the MPU, so it means it's quicker to fetch and quicker to execute. So that's what the instruction cache does. And the data cache is a similar job, temporarily holds the incoming data. Okay, so the word cache, whenever comes in this course or in any other kind of smart systems, that means it's a memory location which is near to the CPU or MPU. Okay, and that is, but the purpose of that is faster execution or to increase the speed of the overall system. Okay, so the CPU, so we talk about the CPU, the major components inside the CPU and an MPU. So, but CPU has to communicate with external devices like RAM, ROM, other external peripherals, right? So to do that, it uses the bus architecture system. So as you can see here in this slide, we have address bus, data bus, and control bus. So you think this as that if you think those blue boxes as houses, CPU, RAM, and ROM, like there are houses, and in order to send some package, mail package between these boxes, so what we do, if a mail you have to send from one home to another, you write addresses, right? That's why the address bus is the data bus is the data inside the envelope, which has to be delivered to the destination. And the control bus, you think this is the delivery mechanism to control the delivery mechanism, like DHL, FedEx, or any other, normally in different societies. So, but in digital world, it's we call it as a control box because we are dealing with all digital signals. So the important thing to realize that every block, like CPU, RAM, ROM, external peripherals, they have a unique address, like serial ports, parallel ports, USB ports, they have unique address. So whenever CPU tries to communicate, it knows which address I need to send or receive information. Okay. So the bus width describe how many conductors comprise the address bus and data bus. So what it means that the size of the address bus can be 8, 16, 32, 64, 128, and similar with the data bus can be 8, 16, 32, 64, 128. So that is what it means by the bus width. And address bus helps the CPU find physical locations in memory, as just said, and data bus transfers data between CPU components such as between IO and RAM. The wider the data bus, the more data that can be transferred at one time. Again, 8, 16, 32, 64, and 128. Very commonly nowadays it is 64 in laptops and CPUs, newer ones. Okay? But historically it was 16. So here I'm going to emphasize some of the important popular buses. So as you can see inside, if you open up the motherboard, you have PCIe buses, which look like, kind of I'm just showing the as a block, PCI bus. ISA bus was kind of longer, different kind of architecture of the bus. Then we have IDE buses, AGP bus, or memory buses. So the buses can be of different types, kinds, and but the entire purpose is basically to communicate between different blocks. Okay, let's carry on. And that's what the instruction set is. As I said, an MPU has a fixed number of instruction sets which it can understand. So, for example, here we are talking about that we want to transfer the data, and here is a manamic, means in assembly language you can use this instructions MOV, but whatever instructions in assembly language you will use, it will, or for example, if you're programming in C or C++ or Python or any other language, whatever line of code you will write, uh, it will get converted into an opcode. An opcode is the code which your MPU can understand, and it will be a language of zeros and ones. Okay, but manamics in assembly language we call it as manamics, or the words which we can write in the assembly language very commonly, and then it gets converted into an opcode. Okay, and that's so for an instruction data transfer. In assembly, we will write it as a manamic MOV, and it gets converted into this opcode, and this opcode is which gets fetched by the CPU for the MPU in order to execute the data transfer instructions or all the other addition, subtraction, multiplication, division, or whatever operation you want to do. And this opcode set is limited. When I say limited, it can be 20 opcodes for an MPU or a CPU, or it can be 50, or can be 100. But it's a limited number of instructions you can do, or you can talk in order to talk to the CPU/MPU. Okay. Now here there are different type of microprocessors or CPUs out there. They are only using in this slide the word microprocessor. It can be any smart chip with brain in it, like a microprocessor or a processor. There are different types. One is CISC. CISC stands for Complex Instruction Set Computer, or it can be RISC, Reduced Instruction Set Computer. So what is the difference? So see, the CISC type of intelligent chips or smart chips uses several math instructions to carry out complex commands. So what that means, that it's basically in order to let's say in order to fetch an incoming data, or in order to to do addition or subtraction, whatever the instruction we are asking it, it's going to take several computing cycles. So it means it will take longer to complete the instructions. That's what it means with this particular sentence. Uses several math instructions to carry out a complex commands. Whereas in RISC, it uses only one instruction for a complex command. What it means that it's only going to execute the instruction in one computing cycle. So it's faster. Again, so let's say for a CISC-based processor or microprocessor, if we're doing an addition operation, it will take, let's say, 10 computing cycles or CPU cycles. So it's taking longer. But in a RISC-based microprocessor, it can only do that in one computing cycle. So in order to achieve higher speed. And that is what is the difference between a CISC and the RISC-based microprocessors or processors. So very important that you be very clear on it. Any questions, please do ask. So let's talk about the memory devices. We already talked about RAM and ROM, and that's exactly what this slide is saying, that internal to the devices for a CPU, you have a RAM type of memory and a random access memory or a read-only memory. We call it as ROM. But if you go further down, I think I found this as very useful for you to introduce to different type of memories. As you can see here, memory can be of primary type or a secondary type. So primary types are mostly on the PCB or um, inside your laptop computers, motherboards. So as you can see here, you have a RAM and a ROM, but within RAM you have a DRAM, SRAM, or SDRAM. DRAM stands for dynamic RAM, SRAM stands for static RAM, static dynamic RAM. Okay, so they are within that there are different type of RAMs, and at a ROM, as you can see here, there are different type of ROMs as well. Okay, and the secondary type of storage is your hard drives or your optical drives, your flash drives, so on and so forth. So very important that you understand the terminologies here, the type of memories, the primary and secondary, the main as RAM and ROM as primary, and within RAM and ROM what are different type of memories, and we will learn as we go to the next slides. And again, the secondary type of storage as well. So the RAM type of memory, there are two kinds. Static RAM, S or called SRAM in short, stores data bits in internal flip-flops. Okay, and flip-flop is basically a digital circuit. That's all what you have to understand. And data remains in the same state until a new data is written over the existing data or power to the chip is turned off. So again, two very important things to know about what is an SRAM. That it's a type of flip-flop or a kind of a digital circuit to store the information, like a bit information, and that information remains there till the power is on, or the new or the new data is overwrites the existing data. Whereas in dynamic RAM, holds binary data in the form of charge capacitors. So it's used charge capacitors. So what is the disadvantage? That it must be refreshed every few microseconds due to the discharge of the capacitors. So why we take that headache of keep the capacitors charged is because of its faster execution time. That's why we use DRAMs. Okay? Faster execution time compared to SRAM. So again, both type of memories has their advantages and disadvantages like any other um, type of a device or a system we talk about. Okay, so let's carry on. And when we talk about read-only memory, there are, these are the some of the keywords we've discussed. Masked ROM or reprogrammable ROM. So how, what are the features in these type of read-only memories? Usually programmed by manufacturer at the factory. Customer must order several thousand chips from a factory, and that's what we mean by masked ROM or pre-programmed ROM, and that's very commonly, inside your laptops, computers, and any smart devices you use is basically use these type of pre-programs or masked ROMs. And programmable ROMs or PROMs are burned only once by the programmer. So I have used it. So either way, when we talk about RAM, I just forgot to tell you this, that the RAM, when you use in your laptops, very commonly they comes as modules. So these are RAM chips, okay, but they're connected as a on the PCB, and here's the RAM. It's a PCI bus which insert inside the laptop or whatever system you're using your RAM in. But when we talk about ROMs, they basically come in the form of chips. Like that's what I'm showing you here. Very commonly, you will find it on the PCB as a one chip or two or a couple of chips. Similarly, some other kind of terms I showed you: erasable programmable ROM or ultraviolet erasable programmable ROM. What is the difference? Programmed by programmer can be erased by placing it under an ultraviolet light. And again, these units comes, we have used it, and you can erase and program these EPROMs or UV EPROMs. And the other one is electrically programmable ROMs, and programmable ROM that is programmed and erased by injecting an electrical current. So rather than doing an ultraviolet So you can electrically erase such EEPROMs as well. Also sometimes call it as E squared PROM, like E2, E2 PROMs. Okay, so another very important term is BIOS, stands for Basic Input Output System. And what it does is basically holds the program which when you power on any smart device like your cell phone, your laptop, your PC, or any other smart device, when you turn on, there is a BIOS contains the program which checks the health of the system, and in case of any problems it reports you before going any further. Like for example, if you have seen your cell phone, sometimes you turn on, you see black screens with errors, and that's what the purpose of that BIOS is. And even sometimes in your laptop, when you're turning it on, you're getting a black screen with errors. That is done by the BIOS. So it's basically the software, very commonly coming from the manufacturer, and it's there. It checks the initial health of the system. If the health is good, then it transfers the control to the operating system, like Android or Windows or Unix or Linux, whatever. But initially, when you turn on, remember this, the BIOS purpose is to check the initial health of the entire system, and then transfer controls to the operating system. And then after that, the operating system frequently does communicate with the BIOS whenever it needs some services from that software from the BIOS. Okay. So as you can see here, on power up, the software in ROM carries out instruction that checks input, output, and other peripheral devices connected to the CPU, serves as communication interface between PLC hardware and PLC program. Let's carry on. So the address decoder unit is, in simple words, is basically whatever block you want to send your package to, the decoding circuit makes sure that only that block is selected. That's what it all means here. So for example, the CPU or the microprocessor wants to communicate with NVRAM. So the address, and decoding circuit here, it's going to make sure that only this NVRAM block is selected and every other block is not selected. And that's when happens. Only then the address, kind of. So first the address comes out, which selects your block, and then the control and the data to make sure that proper communication happens. And that's exactly what the purpose of the address decoding unit is. MP uses address decoder to enable ROM, RAM, IO, or other chips. When the MPU communicates with the chip, only that chip is connected to the address, data, and control lines of the CPU. All the other chips are not selected. Okay, so you can also think of it as this. The address decoding unit is only selecting one chip and disabling all others for communication from microprocessor to that particular block. Peripheral chips, again, are the chips which basically helps communicate with the external devices, also called support chips, used to enable the microprocessor to communicate with the input-output devices or external I/O devices, supports the MPU by performing a different task. And discrete input module is primarily what you see here is that you have an input, like you have a digital input. As you can see here, it can be on and off. Currently, it's off, and since the input is you're talking about 120 volts, very high voltage, okay, and you're using a varistor for this particular input. But to bring this input as 0 and 1 to the digital world, which is low voltage, like what you need to do, okay, you want to make sure, because these on and off can make spikes, and that's why we use a capacitor to eliminate those spikes. Then we rectify it, and then we regulate it. This is the Zener diode for regulation. So since let's say we are only bringing it to the low voltage is 5 volts, so this Zener diode is, let's say, 5 volts. that enables the opto isolator kind of a diode in it. When the diode is on, it means the switch is on, like connected. That light makes this phototransistor conduct, and we get a 1 here. Okay, but in this case it's off, so it means there is no current flow. So no, the transistor will remain off, and we will get a 0. That's what the discrete input module, the main blocks in it look like. So again, if you have done power electronics or some other, I'm pretty sure you'll be clear on it. If not, again, do ask questions, and right now or during office hours. So let's go to the next one. Again, discrete. We're talking about the discrete module. As I explained you here, it's a rectifier, opto isolator, and it's basically just the term octal transceiver means eight input outputs. Okay, full wave rectifier. This is a full wave rectifier, and opto isolator. This is an opto isolator. Further explaining, how we can get high voltage inputs in a PLC system. Let's go to the third one. Again, it's talking about the Zener diode, and in this case, the Zener diode is a plus 5 volts. So it means, what is the purpose of the Zener diode? Let's say if it's 15 volts, then it will hold the 15 volts here. Because it's 120 volts, the full wave rectifier will give around, let's say the Zener diode is not there. So here you will be having roughly around the peak voltage 60 volts if the Zener is not there. But when we put a Zener of, let's say, plus 5 volt here, it only holds plus 5 here and shorts all the other energy to the ground, okay, to the ground loop. And that's why we get the plus 5 as a true when the switch is on. Okay, that's what the slide is telling you. Again, let's talk about the output module. It's kind of a latch, okay, and the octal latch are 8 output ports. The values of those ports remains the same until the new input or new input bits right over there. 2 optical latches are needed to make a 16 output module. Okay, and here's what as an example of a discrete output module, and it's using a triac. And here's the triac. It's basically trying to activate it, and a triac is nothing more than a relay. The solid state relay can be used for switching output voltages on and off in order to connect the load to the AC voltage. So basically, right here we have digital signal here coming from the CPU, like zeros and ones, like plus 5 volts or 0. And we're using an opto oscillator to make this LED to switch this transistor on and off. So let's say we send the signal of 1, which is plus 5 volts. The LED glows, the transistor turns on, and this trigger control for the triac make the triac on in order to deliver 120 volts to the load. Okay. So the modules, as we mentioned here, can be analog, and in the analog modules, there are 2 very important chips inside there. One is called analog to digital converters, which basically converts an analog input signal to digital signal. Like, for example, it can convert our voice into digital signals, or it can convert AC voltages to digital signals. And whereas in digital to analog converter, also called DACs, it basically converts the digital signal back to its analog form. So the 2 very important chips, ADCs and DACs, basically, which comprises the analog I/O modules. Again, here's the final kind of the key block inside the PLC is the PLC power supply, and what it does, it takes the power from the mains, 120 volts in the North American region, and it uses this, after the transformer It uses the full wave rectifier in order to, and the filters in order to, again, transformers, rectifiers, full wave rectifiers, filters, and regulators in order to generate the voltage for the PLC. And the voltage for the PLC is, typically plus 5 volts DC, or it can be 3.3, 2.7, 1.8, and so on and so forth. It can be plus 12 or plus 24, again, depending on the type of PLC you're using, okay, or the kind of rack you have. But typically it's plus 5 volts. And it can also be a minus 5 volt, it can generate. So that's what the feature of the power supply is. We will further go because these blocks are very commonly relating to power electronics, so not we are not going to go deep down into the details of these blocks, but again, um, um, if you are very curious about what they does, please see me during my office hours, and I can explain you when the full AC is coming, and what is the purpose of the transformer and the full wave rectifiers and the filters and the regulators. I already talked to you about the regulator in the previous slide in order to generate the required output voltage. Yeah, so these are kind of the popular PLCs from Allen Bradley, very popular known PLC manufacturers, and are used to implement specific instructions. We already talked about I/O port control, timing, counting, data manipulation, reporting, arithmetics, logic, and communications, and that's how they look like. Sorry, I just totally put a, here you go. And that's and as you can judge, like most of it, they are they are modular. Okay, you can expand it, modular, but in this case it's this can also micro logics, smaller PLC, and yeah, if you put it on the rack, you can also expand these units as well. So they are very kind of popular and modular PLCs. Again, different type of PLCs, depending on what we will have in the lab, we will discuss and focus on those PLCs. Okay. And Allen Bradley, it's just talking about the Allen Bradley series of microcontroller PLCs. And as I said, like we will focus more on the type of PLC we have in the lab. We will be using, practicing during our lab times. And here it's talking about compact logics and control logics controllers. And the important thing is I need to tell you that most of the PLCs, there are different popular softwares, but this RS Logix 5000 software is a popular one we use to program PLCs. Okay, and we will practice it in our lab time to get quite familiar with this software, because we will be heavily using it for programming PLCs. Okay, so another some of the keywords is distributed control systems. So as you can see here, in simple words, a distributed control system that you have different locations. So location 1, 2, and 3. You're using your PLCs, and you're making an architecture and bringing together in a bus for different PCs to monitor all those units. So that's what is called as distributed control system. Many controls are used in different locations, control various parts of the system. Field bus capable of internet connection and other plant control systems. So again, field bus, we will learn about it, what it is, what it can do. So in simple words, these are your field buses. Okay, used in power plants, oil refineries, and chemical production. Why we use a bus? For easy connectivity, easy or cost effectiveness and efficiency in the overall smart system or PLC system. The remote terminal unit, or also called remote telemetry unit, provides multiple communication options for monitoring remote assets such as radio towers or pipelines, links an adapter card to the computer to an I/O with custom control and communication applications. And as I said, so it's basically, as you can see, this is a radio module. There's communication with the towers. In some cases, the symbol here is not a communication tower. It's more very likely a power, power line scanning tower. But again, either way, we can also use power lines for communication. But here we can use cell phone towers. It's all about remotely monitoring, communicating with different locations. Okay, that's what this RTUs we use for. And these are some of the features comparison of different PLCs, like between PLCs, RTUs, distributed control system, and packs. Yeah, so depending on, make sure that when you're selecting a particular device, you make sure that what you're trying to achieve in there is listed as a feature. Okay, that's what this slide is showing you. So what is a field bus? Communication with intelligent industrial controllers. Just-in-time communication delivers relevant information exactly when needed. Field bus allows two-way radio communication between PLCs and other industrial controllers and their I/O devices. So that's just a name. It's a bus in order for easily connecting and communicating with different PLC and I/O devices. But we'll go further down into the details in our lab time to get hands-on knowledge relating to the field bus as well. Okay. Overall, to manage the entire, these PLCs, we use a SCADA system. We call it as Supervisory Control and Data Acquisition System. And the task of the SCADA system is you can think of this as a software which basically monitoring all of your PLCs connecting to different devices. In simple words, that's exactly what the right-hand picture is basically showing you. And some of the tasks of the SCADA system is logging data, tracking process changes, handling data, handling change permissions and access control, process machinery and operations monitored and controlled. SCADA system provides ability to measure and control elements of the first system. Okay, so that's another very important keyword, SCADA. Make sure that you understand the terminology and what SCADA stands for. Okay, and again, this is what the SCADA application is. It's basically everywhere. It's just showing you 4 pictures: one for the sewage plant, mass transit system, power plants, and manufacturing applications. But in simple words, wherever you need smartness, efficiency, cost effectiveness, modularity, reliability in implementing your smart systems, you need to use PLCs, and you need to use associated software, SCADA-like software with it, which is industry kind of a standard, to make sure that your objectives remain safe, secure, efficient, and cost effective. Okay, that's another lecture, and see you in the next lecture. Thank you. Take care.